Okay, so today we're going to look at Chapter 2, Kinematics of Particles, especially focus on force and acceleration. So what you have learned in Chapter 1 previously, we will apply it in the following chapter. Okay, so now in this chapter, we will consider the Newton law. We'll consider Newton law in Chapter 2. So what is important for Chapter 2, you remember F equal to ma. Okay, F equal to ma, which is a Newton's second law of motion, and we apply for all these coordinate system: rectangular, normal, tangential, and cylindrical, and central force motion and space mechanism. All right, so for this module, uh, we will come back to this section if we have time. Means we will study more about this last section if we have time. So again, this is the overview of Chapter 2 objective. With this, we will focus more on the Newton's second law of motion. So no matter how the question will come out for Chapter 2, you just need to remember Newton's second law of motion, which is F equal to ma. Okay, F equal to ma, and we will focus on the acceleration of the particles and also the central force of the motion. Okay, so again, for this module, for the third objective, this one, we will come back if we have time. But we have time to look at the space mechanism. So just recap, what is second Newton law? So second Newton law is focusing on the acceleration of a body. Okay. So there's one word that you will see is kinetics. Kinetic means movement of particles of an object under the effect of force. Okay, under effect of force. So the force will make the body to react, and change the reaction into motion. So recall, this is what you learn in your static module. So you apply the static module, second Newton law, in this section, okay, in this chapter. F equal to ma. And remember, in engineering dynamics, we see force, we see acceleration, we see velocity as a vector. Okay. All right. So force equal to ma. Force is F. M is a mass of that particular body. A is an acceleration. Okay. Now for the in the previous chapter 1, we have come up with a derivation for acceleration, right? So we have studied the displacement, the position of that object, and then we take the information of your position S, we derive, we take the derivative over time, dt, ds dt, we get velocity. So when we get velocity, we differentiate over time again, we get acceleration. Okay, so in this chapter, you need to recall what you learned in chapter 1 and apply in the scenario that we have set up in chapter 2. Okay, so I think this formula you are very familiar. F equal to ma. Only need to remind yourself is the force and acceleration, they are vector. Okay, they are vector. Vector, you have magnitude and direction. So these are the main things that you need to always remind yourself. When you talk about force, you talk about acceleration, you talk about position, you talk about velocity, then all these you can convert into vector. So this is the first equation for today, equation of motion. So second Newton law, also known as equation of motion. F equal to ma. It's a second law of motion. Newton, you have 5 Newton law. So this is one of it. So what is Newton law? Okay, we have clear the first one already. Newton's second law of motion, F equal to ma. Second one, when you talk about gravitational attraction. The gravitational attraction means you consider two bodies that attracts to each other because of the gravity force. So you talk about planet, you talk about something that move in a space that they attracts to each other, and the condition will be vacuum. Huh? When you talk about Newton law of gravitational attraction, your scenario will be in the vacuum scenario, and you study when the two objects that have a gravitational force, and they will attract to each other. So Newton have derived a series of equations for this scenario. Okay, so we can express the Newton law of gravitational attraction with this equation: F equal to G times m1 m2 divided by r squared. So if you look at this diagram here, so you have a body, you take Earth, and a moving body in orbit. We take this object as a satellite. So if you look at this formula, basically we use all the measurable parameter to find the force that attracts to the body. First, in this equation, we need mass 1, mass 2. So you need mass 1 and mass number 2. So it doesn't matter which one is 1, which one is 2, but in this equation, you need two body in the equation. All right. So you label first object m1, the mass of first object m1, second body as m2, and then what is r? R is the position or the radius between between the two body. Okay, so r is the position or the displacement between two body. What is g? G is the constant value that define the gravitational force. Okay, G will change if you change the attraction between two bodies. For example, the sun and the earth, the G will be different. The sun and the Mars will be different, and so on. Okay, so this is the second equation for today. When we talk about Newton law of gravitational attraction, F equal to G m1 m2 divided by r squared. Okay, so basically this is a very direct equation. All right, only one constant value you need to be careful here. So this one we use G, universal value 66.73 times 10 negative 12 meter cube over kilogram second square. Okay, so this is, you apply this one when you're taking Earth, right? We're taking Earth attraction to an asteroid body, or for example satellite or moon, right, to calculate the force, gravitational force between Earth and other object. Okay, any questions so far about this equation? I think it's quite direct. The information is quite direct over here. Okay, again, this kind of question, Newton law of gravitational attraction, we will come back to this one when we have time. Okay, because there's a lot of derivation steps to arrive at this equation. Okay, but anyway, if this question come out in final exam, it's going to be a bonus question where you just substitute the value of the mass of two objects and the radius or the distance between two objects with the constant value given in the question. All right. Any questions so far? Steven, you okay? Okay, Steven, your mic is not working. All right, but I saw some activity in the Teams there. All right. Vinod, are you there? Pranesh, Vinod. Calling Pranesh V0. Okay, just as a record, I'm calling Pranesh V0 or V0 Jaya in a team. Calling V0 in a class, first time. Calling V0 second time. Please respond if you are in the class. Okay, I give you chance. I send message. If you do not respond, I consider you absent in my class. Huh?
Sir, he responded in Teams, sir.
Vinosh, I'm not hearing you. Huh? Your mic is not working. Huh? Okay, let's continue. So we try to derive this equation in terms of weight. So there's a difference between mass and weight. Yeah. So if we talk about weight, we consider gravitational force acting on the mass itself. So mathematically, we take weight as capital W, mass 1, let's say mass 1, M1 as M, and M2, all right, M2 as a mass of Earth, so maybe I switch it M1 as this satellite, M2 as Earth, but anyway, you can switch between the M1 and M2. R is a distance, so we can rewrite this equation in this form. F equal to G, M1 become M, M2 become E, but anyway, you can switch over these two. And we know that weight is mass under gravitational acceleration, W equal to mg. So we're going to write this equation in terms of we can find the relationship of your gravitational acceleration, because if you equal F to W, G M me divided by r squared equal to mg. So F equal to W, M equal to M, then the rest will equal to G. So you get your G equal GME divided by R squared. So this is how you get gravitational acceleration of the Earth. Okay, so this is how you derive the gravitational force for Earth. Huh? We know that our gravitational force for normal engineering application, we use 9.81. Yeah, go ahead.
Yeah, can you explain that again? How W equals mg goes into the first
Okay,
equation?
all right. So you understand from here to here, right? Here to
Yes,
here,
sir.
you understand, right? Okay. Now, if we are standing on the Earth here, and all the object under gravitational force, you can calculate as W, right? So if you have an object of mass with an M under gravitational force, the product of mass multiplied by gravitational force acceleration, you get weight, right? You get the weight. Weight is kind of force, right? So force equal to W, and this is the product, right? Gm me divided by r squared is a mathematics products. So if you compare side by side, this mathematic model, this mathematics products equal to mg. So what is your g? Right? What is your g? Your m equal to m. So this one is you factor the m outside. Can you see your g equal to g me divided by r squared?
Okay, yeah, I see it now.
Yeah, so it is a mathematics direct comparison. Okay, so this is how you derive the gravitational force using the Newton law of gravitational attraction. Okay, so if you're interested in astrodynamics, aerospace engineering, or satellite engineering, then this equation is the fundamentals of all the calculation when you involve in the satellite launch or mission operation. Yeah? Okay, so this equation, it explains what happened on the Earth. For dynamics question, we always assume that acceleration is always pointing going down with a magnitude of 9.81 meter over second squared. Acceleration always pointing down when we consider gravitational force, gravitational acceleration, and all the subject on Earth, you have a mass, or any physical body, you will always have a mass in the unit of kilogram. And where is your weight acting on is at the center point of your object, or we call it center of gravity, CG point of your object, or you can call it as a balance point of your object. Okay, so how do you know the object balance point? Let's say you take an object and then you put a datum in that area and you let go, the object can stay in this position without any movement. That is your CG point. Okay, and I think in the later in your senior years, in other module, when you go into a dynamic class or finite element analysis, you will come across a term called second moment of inertia. Then you will be focusing on this location, right? So anyway, for this module, what is important is that when you come into chapter 2, we talk about moment, talk about second Newton law, F equal to ma. The first schematic diagram that you draw in your answer is this component. Okay, you always consider when you want to solve a question using second Newton law of motion, you will always consider weight in your question. All right, so this will be the first component you draw in your answer. You always go to the object, find the center point, and draw a downwards force represent weight in your solution, okay, in your answer. So this slide basically we talk about gravitational effect. However, this diagram will help you to score some point when you solve question that related to second law of motion later on. Okay, so just a reminder. So you have seen a few equations today. So this is the first diagram that you see, I think the third diagram you see for today. So when you solve question for second Newton law of motion, this will be the first force that you draw in your diagram. Okay, especially the object is inside the Earth scenario. Okay. Next, we're going to look at equation of motion, which is F equal to ma. Okay, so F equal to ma, we start with the force component first. So recall what we have learned in chapter 1 when we talk about vector. So when you have an object, this one, let's say we have particles around body, and you're acting with multiple forces. In this case, we only have two. So F1 in this direction, F2 in that direction. And this is a vector. Vector have magnitude. How you represent vector? With the length of the arrow And where is the direction? Is from the tail until the arrowhead of the arrow. This represents vector, right? Magnitude and direction, you get vector. So this object is subject to two different forces, and you know that you can combine these two forces become resultant forces, right? So you have learned how to combine vector in your calculus or advanced mathematics class. So you combine two vector, you use rectangular or triangular methods to form the reaction resultant force. So we have seen this one in chapter 1 before, right? So you get a resultant force we label as F sub R. Okay, so this is called vector diagram that we have covered in chapter 1. So in mathematically, how you write the equation. So your resultant force is the addition of all the vector acting on the object. So mathematics, how you write the vector summation. Fr equal to some symbol F, means all the force acting on the object equal F1 plus F2. Okay, or you move this vector over here, you get from starting point F2, continue F1, end point, starting point to end point, you get Fr. That's where you learn about the vector diagram. Any questions so far for this mathematics model? Vector summation. Any question?
So far, no, sir.
Good, eh? All right. So we can say when you combine these two vectors into resultant forces, we can draw our diagram. We can represent the earlier two forces and the object diagram with this diagram. Okay, object and the resultant force vector. Okay, so we start to enter into equation of motion. When you draw object later on, when you solve question for chapter 2, when you use equation of motion, you will see that your diagram have two dimensions. One on the left hand side represent all the forces acting on the object, and the right hand side of your equation will be equal to MA. Okay, so this is the strategy when you solve question for chapter 2, F equal MA. So this is how you show your answer in schematic or diagram. Okay, so on the left hand side is forces, on the right hand side is MA. F equal MA. So again, you need two diagrams to solve chapter 2 question or second Newton second motion equation, right? Second law of Newton, right? F equal to ma. You need two diagrams. One is forces diagram, another one is motion diagram, or I call it kinematics diagram. So you need two. So and then as we advance further, I will combine these two diagrams into one. Okay, so later I will show you one example, and then as we advance further, because we have a limited time when you answer question, so I will combine the kinematics component inside same diagram. But in your mind map, when you solve question, you have two different diagrams you need to pay attention to. So today, when you solve question, when you use F equal to ma equation to solve, remember you have two diagrams you need to draw, or you can split your answer sheet into half. One you solve for the forces, one you solve for the kinetic motion. All right, so there's a name for that. In the question itself, maybe sometimes we will guide you. we will ask you to draw free body diagram, meaning, what I mean by free body diagram? Meaning you draw a body with all the forces related in the scenario. And the question will ask you to sketch a kinetic diagram, which is only consider the kinetic or motion of the object. What I mean by motion? With this acceleration. Okay. So at this point, we introduce you again what is free body diagram, what is kinetic diagram. Okay, try to differentiate these two. Free body diagram, you only solve for forces. Kinetic diagram, you solve for acceleration. Okay, so far, any question? Now we move forward. So again, introduce you the equation of motion, F equal ma. So this basically is the steps that you will see for your tutorial question. First, you read the question. Second, you draw the schematics diagram for the question. Your sketching or your diagram will consist of two diagrams. One is free body diagram on the left-hand side and kinetic diagram on the right-hand side. And you solve free body diagram for the forces, meaning you expand all the forces to force to the y-axis and x-axis, or horizontal axis or vertical axis, or normal axis or tangent axis, right? So this is what you do. And then on the right hand side, this one, you solve for all the accelerations related questions. So then after that, you combine these two together, you solve for the missing parameter. Okay, so this basically is very important slides that help you to solve equation of motion kind of question, right? Important, this equation, F equal to ma. And we'll talk about the strategy to solve equation of motion kind of question. Next, we introduce you a reference frame. Okay. What I mean by reference plane? Let's say you have a particles that moving in a straight line. The particles moving in a straight line, and in this module, we will use blue color to represent the path and the direction of your acceleration in your kinematic diagram will always same direction as the particle movement. I repeat again. When you draw diagram for, okay, when you draw diagram, there are two diagrams you need to draw. One is free body diagram and kinetic diagram. Your kinetic diagram, your A, especially the arrow, will always same direction with the motion of your body. Example, you take these particles, this particle moved from left to right. So the positive direction of your acceleration will be from the left to right, will be positive. So all the motion to the right will be positive. Okay, and when we talk about reference plane, means you are standing there without moving, and the point of the observer we mark as origin O, and we give axis X and axis Y. And when this object moves in the horizontal, this object doesn't move. So there is a reference velocity we name as VO for these particles. Okay, but anyway, you will see how we apply this one in example later on. Next one, this is two-dimensional. Okay, this is two-dimensional where you only have y and x. This is for solving a motion inside a space. So if we talk about a liquid, molecule, and we only capture one of the molecule inside the system here. Okay, so before you start solve question, you look at the system. So in this case, you have three-dimensional scenario here. You have x-axis, y-axis, and z-axis. And we assume that you are looking at a drop of water that being flown or being pushed with a force, and it act upon it. So you have imaginary boundaries of this dashed line, and you pick one body, one particles inside this system. We call it I, particle I inside this system. Okay, inside this system, we pick one element or one particles, we label as I, and there's a force acting on this element, and we apply what we learned in chapter 1. When we have a reference point, we can measure the origin to the body. We put as position Ri. R sub I means the position from the reference plane to the particles. And then there is a G. Okay, there's a G position also. And there's a small f there. So let's look at these particles. So this particle I, you have two forces acting on it. So what you do when you solve this kind of question, you focus on that particular object or element. You draw two diagrams. Free body diagram on the left, kinematics diagram on the right. Left equal to right. Okay, you draw two diagrams, free body diagram and kinetic diagram. You equal the two diagrams by using second Newton law, F equal ma. Okay, so on the left hand side, the free body diagram is only consider all the forces acting on that particular object. In this case, you have Fi and small fi equal to ma. So ma, these particles, when we study the vector, the resultant vector between these two, when you combine these two vectors together, you get a direction from the beginning until the end. Right? You can build a vector diagram over here. You know that the resultant force is in this direction. I hope you can imagine and see and follow my finger. You can see that there's a resultant force from the beginning until the end. Okay, you need to know how to apply the vector diagram over here. Okay, you have two vectors, 1 and 2. You combine these two vectors by using diagram. How you combine vector, this one plus this one, how you get the resultant from the beginning until the end of all the vector combined together, here to here. That's why you get the arrow pointing in this direction. Okay, yeah? So basically you can estimate the direction of your motion for your kinetic diagram if it's not given in the question. Right? By looking at the force itself, you can know where is the acceleration will be. Okay, so in this case, acceleration is pointing downwards, and we label as MI EI. Any questions so far?
Hello, sir.
Good, all right.
Hello.
So, yeah, go ahead if you have any question.
So these diagrams don't show the plane that the object is in, whether it's two-dimensional or three-dimensional.
So in this scenario, we are having, in this case, since you are seeing the three axes there, it's a three-dimensional question.
Okay, so that one will be given inside the question.
Yeah. So now you look at the individual particles, really this one, and then you collect all the forces on that particles only.
Okay.
Okay,
understand.
yeah, all right. Then you convert into F equal to MA diagram. F is the free body diagram on the left hand side, equal MA. MA is a kinetic diagram. So this is the skill that you need to, a strategy that you need to know when you solve F equal to MA kind of question. You look at the scenario, copy the position or copy the object, then you consider all the force on the object, draw free body diagram, then you look at the diagram. Sometimes the acceleration will be given. If acceleration not given, you can estimate the direction of the particles, right, from that scenario. Right? In this case, we know that A is in this direction. So all these are some explanation about the small f and big F. Okay. So when we have two diagrams, free body diagram on the left, kinematic diagram on the right, we can solve by using this mathematics equation, all the force equal to ma. So in this case, we can write capital Fi plus small fi equal to mi ai. We use second Newton law of equation of motion, combined with the diagram, we come up with this equation. Okay. Next, because this is only one particles, and we talk about whole body as a sum of forces energy. So what we do, we will use summation in mathematics form. So all the force acting on particles I and all the internal force, we use this symbol, equal to all the kinematics forces on the right hand side. Meaning this equation is only focused on one particles. And if you want to find the whole system, what happened to the whole system, you will add a summation symbol just beside the forces. Okay? Because this is one, so you want to find all, you just add a summation symbol like this. This one also. And this one also. Okay? All right. So in this case, our internal forces will be equal to 0 because there's no energy given or there's no heat created in the particles. So in this case, we write all the internal forces equal 0. In this case, we are not using uranium, we are not using self-generated, heat-generated mechanism inside the body. So there's no internal forces that can convert into kinetic energy. So our internal forces will equal 0. In this case, we assume that this body do not have a self-generation or self-energy, there's no mechanism inside these particles that help to generate energy. For example, this is just a normal metals particles that do not generate any energy. But if this is a uranium radiation particles, then internal forces is not 0. So in this case, we just assume we have maybe drop of water that do not generate energy. So we can write all the forces equal to ma. Now we talk about center of mass in this case, which is your G. If your Rg is a position vector, your Rg is a position vector that focuses on the center of mass. So how do you calculate the center of mass? All right. Okay, G here is the center of mass of this whole liquid, you can see this as a liquid, right? Or this whole element here, right? And you ignore all the small forces here, right? So how do you find the center of that body? You learn about this one in your physics. When you find the center of mass, what you do, you take, on the left hand side, you take mass multiplied by rg, which is the radius or the position to the center of mass, equal to all the mass multiplied by the small ri, which is individual. Ri means from the reference point to the individual. This is the equation we use to find the center of mass. Okay, this is the equation we use to find the center of mass of a system. On the left hand side is a bigger picture. M equal to Rg means mass multiplied by the position of the mass, which is from the reference point to the center of gravity, equal to the sum of all the particles that scattered in the system. Okay. And you know that this mass, if you add all the mass of individual, right, if you, on the right hand side of the mathematics model here, if you add all the mass of individual particles inside the system, what do you get? You'll get the same mass m here, right? If you add all the individual particles inside the system, you'll get the same mass of the whole system. So this one equal to this one. And then you differentiate over time. Okay, recall, this is a step that we learned in chapter 1. When we have a position, we differentiate over time, we get velocity. Okay? And we differentiate one more time, the position means we differentiate 2 times over times, we get acceleration. We will get m. M is a constant. You differentiate over time, your position become acceleration. This one, your position become acceleration. Again, for mathematics dimension, on the left hand side, you focus on the G point or your center of gravity. And on the right hand side, your equation, you focus on individual particles. You arrive at MAG equal to sum of MI AI equation. Okay. You know, from here, you apply equation of motion, F equal to MA. This one equal to F. Okay, so you know that this one, you know that all the force, okay, this one, all the force equal to MA. So you substitute this one as this equation. You can write this equation into here by writing sum of Fi equal to MAG. What does this equation tell you or prove to you is that you can straight away use F equal to MA, force acting on that particular object, or on the left hand side, you can use the free body diagram equal to MAG means the acceleration of the whole system rather than look at into individual particles. So F equal to MA equation is proven using this diagram. Okay, we stop here for a short break. I stop the recording.